couple of definitions for you. Guys, what would be monoprotic acid? Mono is one, right? Any acid which can dissociate, produce 1 mole of hydrogen ion from 1 molar acid, or any acid which can dissociate 100% in water, and all the hydrogen ion is coming off, and it can produce only one, it has only 1 hydrogen ion on the molecular structure. We say monoprotic acid. Why do we call HCl monoprotic acid? Because it can deliver only 1 acidic hydrogen. Why would we call nitric acid a monoprotic acid? Because it can produce 1 hydrogen ion. Are there acids which have more than 1 hydrogen ion? Yes. Well, this is not the example yet. This is still monoprotic acid. Only this hydrogen is ionizable. The other hydrogens are not. So it can produce 1 hydrogen ion. So it's called monoprotic acid. However, this is a weak acid. These other two monoprotic acid are strong acids. So if I continue going to the next slide, there are diprotic acid. Do you see sulfuric acid has got 2 acidic protons? The first proton, the first hydrogen ion can come 100%. So sulfuric acid is strong acid in releasing its first proton. The second proton coming off through partial ionization. So this acid has less tendency to lose its second proton. It only dissociates partially. So I can say this is a weak acid because its proton is not coming 100% off. It's coming off through an equilibrium. This is a strong acid. Why? Because we have got 100% dissociation. And is there such a thing as triprotic acid? Yes. Example of a triprotic acid, if you look at the structure of phosphoric acid, it has got 3 acidic hydrogens. And based on experimentation, we know phosphoric acid is a weak acid. What does that mean? It means all 3 hydrogens are coming off through an equilibrium. First one hydrogen comes off to give you H2 PO4 minus. Next, the second hydrogen can come off much less than the first hydrogen. We have got an equilibrium which is much weaker than, let's say, equilibrium 1 has K1, equilibrium 2 has got K2 for dissociation, and even the third hydrogen comes off in less than K2 and K1. So the equilibriums are getting weaker and weaker. Equilibrium number 1 is the strongest, goes more toward right than number 2. Number 2 goes more toward right than number 3. So this is a triprotic acid, but it's a weak acid. So 3 hydrogens, triprotic acid, 2 hydrogens, 2 acidic hydrogens, diprotic acid, 1 acidic hydrogen is monoprotic acid. So guys, if we are talking about the solution and we say this solution acidic or basic, we can have several different acidic solutions. Some could be more acidic than other acidic solutions. You might have several basic solutions which have different degree of basicity. So I need a system of quantification, a number that I can give you and tell you this is the degree of acidity of this solution. So how do we do that? We are doing that by pH. pH is defined as negative log of hydrogen ion. So I can give you a number which can show how acidic the solution is or how basic the solution is. So by definition, we define a neutral solution, which is a freshly distilled water. In freshly distilled water, concentration of hydrogen ion and hydroxide ion are equal together, and the pH of this solution at 25 degrees of Celsius, we call that room temperature. We define that to be room temperature. pH is 7. So that's our definition for a neutral solution. It's a solution which has a pH of 7. It means hydrogen ion concentration is equal to 1 times 10 to minus 7. Why? Because if I say pH is equal to minus log of hydrogen ion concentration, which is 1 times 10 to minus 7, you can use your calculator, take a log of 1 times 10 to minus 7. This is the number you get. So if a solution has a pH of 7, we call that neutral solution. So again, by definition, any solution which has got more hydrogen ion than hydroxide ion, we call that solution acidic. And at room temperature, hydrogen ion concentration in an acidic solution is larger than 1 times 10 to minus 7. That means if I take negative log of that, you get this conclusion: any solution which has pH smaller than 7 is acidic. So pH 6 is acidic, pH 5 is acidic, pH 4 is acidic, pH 3 is acidic. That's pH of tomato juice, actually. Or pH coffee is somewhere here between 4 and 5. So any solution which has got pH smaller than 7, it's acidic. Then what would be the definition of a basic solution? The basic solution is a solution where there is more hydroxide ion than hydrogen ion. And what does this mean in terms of concentration of hydrogen ion? It should be less than 10 to minus 7. And if you take a negative log of any hydrogen ion concentration, which is smaller than 1 times 10 to minus 7, you're going to see the pH goes higher than 7. So pH 8, pH 9, pH 10, pH 11, so on and so forth. These are all basic solutions. So now we have a number to say how acidic solution is and how basic solution is. And if we have two acidic solutions, we can tell you which is more acidic, which is less acidic. How do we do that? By use of pH scale. Now, pH scale can be measured. Some of you use it in Chem 2A. You have seen the picture. I'll show you a picture. We are doing a video. We measure the pH using a pH meter. So you will see how pH meter can be used to determine the pH of a solution. Based on that number, we can tell whether solution is acidic or basic, and what is the scale of acidity or basicity. So is it fair to say as pH goes up, hydrogen ion goes down? Why? Do you see there is a negative here? So pH is equal to negative log of hydrogen ion. So these are inversely related. As pH goes up, solution becomes more basic and hydrogen ion concentration drops. All right, so these are some examples. Gastric juice has a pH between 1 and 2, or stomach acid. Lemon juice, pH 2.4. Vinegar, pH 3. Grapefruit, pH 3.2. Orange juice, pH 3.5. Urine, pH range 4.8 to 7.5. So water, if you distill water, immediately distill, it's 7. Let it stand in the air, it's going to absorb carbon dioxide from air. It makes carbonic acid. It becomes acidic. So water which is exposed to air is not pH 7, pH 5.45 or around that. So saliva, 6.4 to 6.9. Pure water, freshly distilled water, is pH 7. Household ammonia is basic, pH 11.5. Milk of magnesia is anti-acid. It is basic, pH 10.6. Guys, the same way I define pH as negative log of hydrogen ion, the word P in chemistry means minus log. If I say POH, it's minus log of OH minus. If I say pH, it's minus log. Minus log of hydrogen ion. So you can determine pH and POH of a given solution. We also told you that the value of equilibrium constant for autoprotolysis, the value of equilibrium constant for exchange of hydrogen ion between two other molecules, the value of this constant at room temperature is 1.0 times 10 to minus 14. And we also said that for any aqueous solution, anywhere you have water as the solvent or pure water, there is always enough hydrogen ion and enough hydroxide ion that if you multiply concentration of these two, is always going to be fixed amount at room temperature is going to be 1.0 times 10 to minus 14. So if I take a log from this equation, if I take a log from both sides of this equation, I get negative log of hydrogen ion minus negative log of hydroxide ion and log of this. What is log? What is log of 1 times 10 to minus 14? Can you guess? It's going to be 14. You can check your calculator. So can I develop an equation now? Did I say this is pH? And did I say this is POH? So I can make this equation that pH and POH for any aqueous solution is going to always be related together by adding them to be equal to 14. So now you have a formula to relate these two together. So if I say pH is 2, pH of a solution is 2, so what is POH? So it's a number which is added to 2 to be 14. Another word, can I say pH is equal to 14 minus POH? Can I say that? Or the other way around, POH is always equal to 14 minus pH. So these two, pH and POH, are related together by this equation. I hope this makes sense. If it doesn't, please make sure to come and see me so I can explain these to you in person.